Welcome everybody to today's webinar. It's a great pleasure for me to introduce today's speaker, Phebe Vayanos from US. Now we have someone from California, and that's a very nice thing. So Phoebe got her PhD from Imperial College London. She joined MIT then as a postdoc and lecturer right after her PhD. And then after that period, she started as an assistant professor at the University of Southern California, where she is now as an associate professor in the Department of Industrial and System Engineering and Computer Science. Her research is on the overlap of optimization and machine learning with the focus on applications toward the societies and societal good. She has received many awards, and including the NSF Career Award and Informs Diversity, Equity, and Inclusion Ambassador Program Award. So it's a great pleasure to have you, Phoebe, in our webinar. And without further ado, I would like to hand you the mic and the screen.
Thanks so much for the kind introduction, Reza, and thanks to both you and Yanis for organizing this series and for inviting me. I'm really excited to be here to share a little bit about our work. So today, what I'll be talking about is our work on learning classification trees that are going to be robust to distribution shifts. And this is work led by my PhD student, Nathan Justin, and in collaboration with my PhD student, Sina Agae, and my close collaborator and colleague at USC, Andres Gomez. And feel free to interrupt with questions as we go. So I have a pretty standard outline for my talk. I'll start by motivating a little bit the problem I'm looking at and what's made me interested in it. I'll then go ahead and formulate my problem mathematically, propose a solution approach, and then discuss some numerical results. So what got me interested in this problem is a problem I encountered in my partnership with the Los Angeles Homeless Services Authority, which is the ANT for short. So this is, so with LASA, we have a project in collaboration with many other organizations, including UCLA, the California Policy Lab, the University of Missouri. This is us meeting with LASA a few years back. And what's interesting about this project is actually it brings together collaborators from many different fields. In particular, it involves social scientists, data scientists, and computer scientists, and we even have put together a community advisory board to help inform the research that we do. So before telling you the problem, let me give you a little bit of background about homelessness in Los Angeles. So homelessness in LA is a huge problem. There's over 69,000 persons experiencing homelessness as of 2022. And there's not enough housing resources to help support those individuals. We have about 28,000 units. And there's different kinds of units. Broadly speaking, we can categorize them in two types. One that's more supportive, called permanent supportive housing, which is a long-term intervention that provides both housing and support services. You can think of services like mental health services and whatnot. And then we have kind of less supportive intervention called rapid rehousing, or RRH for short. And the vast majority of people, just because there's not enough resources to go around, will receive services only, supportive services, basically. So now how does it work? How is it decided what kind of resources you get is based on this scoring tool called the VICDAT, or Vulnerability Index and Service Prioritization and Decision Assistance tool, quite a mouthful. Wherein basically you come into the system and you fill in this very lengthy survey that perhaps a social worker on the street helps you take and whatnot. This survey is asking you relatively personal questions related to history of housing and homelessness, risks, socialization, daily functioning, wellness, And so depending on how you answer each of the questions on the survey, you get a score for that questions. All the scores are added up together, and they're used to give your vulnerability score. This vulnerability score is basically meant to predict adverse outcomes under no housing. Roughly speaking, although it was not built in a data-driven fashion, that's the intention. And this survey, basically both the answers to the questions and then the vulnerability score are used to decide what services you will receive. They're used for triage, for prioritization, and so on. So now back to our project with LASA. In this project, there were three types of things we were looking at. One was actually the assessment, which is this survey that I mentioned, that is looking precisely at the question, the choice of the words, the length of the questions, the order. So this is a kind of qualitative analysis of the survey, aimed to see, well, is it possible to improve it? And same for administration. In the administration, it's looking really at the process. When, where, how is the survey conducted? Are we comfortable with how things are done? So these first two aspects are really qualitative, and we're working with the community advisory board to help improve this thing. On my end, though, I'm really focused on like the data side of things, which is really, are we comfortable with the way the scoring is done? Is it really predictive of adverse outcomes? Are we matching in the right way? So meaning, is it really the decisions to who should get these very scarce resources? Are they done in a good way, and so on? Can we improve them? So what is the issue here is that, well, we have these two kind of the qualitative and quantitative sides of the team that are making. Let's begin a little bit deeper into the questions here. So here I have a bird's eye view of the survey, and let me zoom into a couple of items. So the first item is asking, do you ever do things that may be considered to be risky, like exchange sex for money, run drugs for someone, have unprotected sex with someone you don't know, share a needle, or anything like that? So a few observations about this. This is a current survey, right? It's asking very personal questions. It's a little bit ambiguous the way things are asked, right? It says, or anything like that. What one person interprets as or anything like that may be different than what someone else interprets as when I say or anything like that. I may get this question from someone I haven't met before on the street in an environment where I'm perhaps not comfortable, right? So these are things we're looking to change on the qualitative side. And this question is kind of not a one-off. I can zoom in on a different one. Here it says, are you currently able to take care of basic needs like bathing, changing clothes, using a restroom, getting food and clean water, and other things like that? So also these questions, right, they're asked with good intentions. They are very personal. And so now, because the qualitative part of our team is going to try to rephrase, right, improve the administration of the tool and the phrasing of the questions and whatnot, the expectation is that perhaps it will change how people respond, right? Maybe things are done in a better way from someone I have interacted with in the past and so on. Perhaps I will be more comfortable sharing past experiences with them. So how is that a problem? Where us on the data side, right, we're using this historical data that was collected in a particular way to train our model. And today I will really talk just about prediction tasks, but we imagine that similar things hold in the prescriptive setting. So we're taking our training data, we're learning our models, and then our intention is to deploy, right? And so now if I deploy and the data in deployment looks very different because we have gone and changed the way in which we collect the data, which presumably changes the distribution in which the distribution of the data, it's not clear that our models will perform as expected, right? And so this is the problem I'm interested in addressing today. Let's see if it's really a problem. So what we did here is we took data, just one data set from the UCI machine learning repository. And we trained, in this case, a classification tree, and we evaluated it. And we got this yellow line that, you know, we expect that in the test set, we will have a performance of an accuracy of 87%. Now what we did is we took that test set, the same test set, and we perturbed it. So meaning we changed a few of the entries with some probabilities, and we did that exercise. Okay? And for each of those 100 times, we recorded the accuracy of our model on the test set. What we see now is, and so here what I'm plotting is basically this distribution of accuracies over those generated test sets. And we see that actually, more often than not, the accuracy that I get is lower than what I expected. And this is really due to this distribution shift issue. So when the distribution of my deployment data is different than that of my training data, I don't have guarantees anymore, and my model may perform quite poorly. Are there any questions so far? All right. So I've talked about robustness here. Really, what I would like is that my model should work well, even under distribution shifts, and even when those shifts, I don't have a whole lot of information about them, right? So I'm going to want robustness. This is going to be particularly important in the high stakes domain that I mentioned, for example, because basically, if my model is not as accurate as I expected, what is happening is that I'm incorrectly predicting vulnerability. So if I'm using this vulnerability score to match people to resources, it's a problem. It means I'm prioritizing the wrong people. Similarly, we want optimality, right? I'm working backwards here. Indeed, when we're working in high stakes domains like the one I talked about before, but in many other domains as well, any little bit matters, right? Every improvement I can have in terms of accuracy or in terms of the decision quality is important. So we're trying to look here for optimal solutions to our ML problems. Something I have not yet discussed, but that is again important in this high stakes domain, is interpretability. So being able to design models where I don't need to explain how they work, they can easily be implemented. One can easily see whether they're doing things that kind of make sense, right? And so this will motivate me basically to look at a specific class of interpretable machine learning models, which are going to be classification trees. An important consideration here is that the data we have received from LASA and in most often kind of societal domains is actually discrete. So all of our covariates are typically discrete, either integer or categorical. We rarely have real valued entries. Perhaps age is one I can think of, where perhaps you can treat it as being real valued, but in general, all of our covariates are discrete. And so we'd really like to have a model that will work with discrete data. So for this talk today, I'll focus on a specific interpretable machine learning model, although there are others that it's interesting to look at. This model will be a classification tree. So what's a classification tree? In a classification tree, we have like a binary tree, basically. And at each node of the tree, we're making a test. If the answer to the test is yes, the data point will be routed right. If it is no, it will be routed left. The test is typically like a condition on one of the covariates. It asks, for example, well, is your age greater than 18? And you can decide the feature and the branching level of the feature. This ensures that each data point is routed to one and only one leaf of the tree. At that leaf, we make a prediction, the same one for all data points that land at that leaf. We will say that the data point is correctly classified if the label of the data point matches that assigned at the leaf where it lands. And our goal will be to learn optimal trees in the sense that they will have the greatest possible accuracy, where accuracy just computes the total number of correctly classified data points. But this time we're going to try and maximize accuracy under adversarial perturbations of the data to make sure that we will perform well even under shifts in the data. In order to do this, we're going to blend basically integer optimization that's going to enable us to have great modeling power, for example, to be able to capture fairness constraints in the long run and things like that, and being able to retrieve optimal solutions to our problem. We'll blend this with robust optimization in order to ensure that our model will perform well even under unanticipated distribution shifts, where perhaps I don't know exactly how the shift will happen, okay? Nor the distribution of the shift. So let me now move on to the formulation of our problem. Let me start with a bit of notation. So I have access here to training data. My data points are indexed in this set calligraphic I. And for each data point, I have access to its covariates, which I denote by the vector xi, and its label, which I denote with the quantity yi. Here, I'm going to assume that my covariates are all integer. This is without loss of generality, just to simplify things in my presentation. In the paper, we analyze the cases of categorical data, bounded integer data, and whatnot. Let me now introduce our perturbations. So the perturbations, I'm going to denote them by this vector xi. So xi is a perturbation applied to the covariates xi. So this is going to be basically represent the shift in the covariate. So in my application, think of this as changes to the responses to the VI-SPDAT survey. And my goal now is to identify the best binary decision tree classifier from the set of all classification trees of maximum depth D. So this is going to be, I'm going to denote this by pi, which is nothing more than a mapping in the form of a tree from the space of covariates to the space of labels. And here I'm dealing with a classification problem, so the space of labels is actually finite. So let me now formulate my problem and hopefully convince you that this is the right problem to look at. So here we're trying to identify the tree pi that's going to maximize the worst case accuracy. How do I calculate accuracy? I sum across all data points. What's the quantity 1 if the prediction from my tree matches the label I see in the data? How do I take the prediction from the tree? Well, instead of feeding it the unperturbed covariate xi, I feed in the perturbed covariate xi plus xi. Why is that? Because tomorrow, when I go and deploy my machine learning model, right, I will see perturbed data, right? I will see data that comes from a different distribution, right? And what I would like, and if I implement it, this tree will return predictions based on those perturbed observations. I don't know what the unperturbed data looks like, right? So are you all convinced this is the problem I want to look at?
Phoebe, there is this question about, I'm guessing, about the uncertainty set. Is it bounded?
Oh, so yeah, I'll talk about this in a moment. Okay. About our model for uncertainty set in a moment. Good question. Yeah. So I'm emphasizing here, if you're happy that we're looking at this model, because there exist other models in the literature that basically solve a different model. So I'm happy to talk about that later in case there's a question about it. So now let's talk a little bit about the difficulty of solving this problem. So we're optimizing here over a space of functions that are nonlinear, discontinuous. The uncertainty set C is discrete. Why is that? Because my covariates are discrete and therefore the perturbations must be discrete. Otherwise, I would have unrealistic realizations of the perturbed data. And my objective function is also nonlinear, discontinuous. So this problem is kind of difficult. Okay, so the first thing we're going to do is actually, let me give you a little bit the big picture of what we're going to do here. And let me go back one slide. What we're going to do is I'm going to show you that this set, this optimization, I can write it as an optimization over integers. And then I'm going to show you that this objective function, which look very complicated, I can write it as the optimal value of a maximum flow problem. Okay. So let's do this step by step. So now I'm first going to look at encoding the tree using integer optimization. Remember, I'm optimizing over trees where we're allowed to stop early, meaning that we can make a prediction at an internal node of a tree, in which case you can think of pruning out any descendants. And so my decisions at the internal nodes of the tree are either I can branch, in which case I need to choose a feature to branch on and a level for the feature. Alternatively, I can decide to predict a class. For example, if I predict at node 1, then I don't care about what happens in the rest of the tree. Or I must have predicted in one of the ancestors. For example, if I'm at node 3, I may have predicted at node 1, and therefore I kind of don't care what happens at node 3. Okay? At the terminal nodes, which are the green nodes here, we can either predict a class, or we must have predicted in one of the ancestors, in which case that node is pruned out. Any questions about this? All right, so we can encode, now based on these observations, we can encode our tree using integer optimization with 3 sets of decision variables. My branching variable is b, so here bnf theta is 1 if and only if at node n I branch on feature f at level theta. Vn will be 1 if and only if I make a prediction at node n, and w and k will be 1 if and only if I predict class k at node n. Okay, so the constraints are fairly straightforward. The first one says that at all internal nodes of the tree, I must either branch on a feature at a level or make a prediction, or I must have predicted at one of the ancestors. At all leaf nodes, I must either predict or I must have predicted at one of the ancestors. And at all nodes in the tree, if I make a prediction at the node, I must predict one of the classes. Okay? So there's a one-to-one mapping now between elements in this set and the trees in Phebe that I introduced earlier. So these trees of maximum depth B. All right, so there was a question about the uncertainty set. So our uncertainty set is actually going to build a ball around the nominal data. So first observation is that all of our, so here the vector xi collects all the xi I, so the perturbations to all of the data points. We require these xi to be discrete, to be integer in particular. And now we're going to have an uncertainty set that is over all data points and features. Basically, it's going to bound deviations from the data, right? The xi represents deviation from the data. We're going to allow different features and data points to have a different cost of deviation. This is particularly relevant when you have different degrees of certitude for different features or data points. Perhaps, for example, in the VICDAT survey, we expect that people from marginalized community are more likely to reveal the truth under this a more sensitive survey. Using classical like robust optimization, we're going to bound this uncertainty for a budget of uncertainty epsilon. Now I'm being a little bit abstract. I will show you in a moment how we can calibrate those gamma FIs using hypothesis testing. All right, so we did this first part of rewriting the over the outer maximization problem using integer optimization. Now what I'm going to focus on is writing the accuracy for a fixed tree and perturbation using integer optimization. In particular, I will show you that it can be expressed as the optimal value of a maximum flow problem. This idea is based on a previous paper we have on learning optimal classification trees without robustness. Okay? So the idea is the following. We take our tree. I'm going to illustrate it on a tree of depth 2 here, this idea. We're going to attach to the root node of our tree a source node, and to all nodes in our tree a sink node. And we're going to direct all edges from top to bottom to indicate that our data points should flow from the top part of the tree to the bottom part of the tree. The idea here at the high level is that we're going to associate with each data point a flow of 1, and we're going to see if a data point can reach the sink. Only data points that are correctly classified will be allowed to reach the sink. So how do we do this? We do this by building a subgraph of this graph for each data point, where the capacities are going to be set to 0 for all links that the data point cannot traverse, is not allowed to traverse, and to 1 to all links that the data point is allowed to traverse. How do we decide whether a data point is allowed to traverse a link or not? Well, as follows. Focus here on the picture on the left. For each data point, if we have a branching node, right? If it's a branching node, the data point can only go left or right. Whether it goes left or right, it's determined by the features that we have branched on, right? That we have decided to branch on, and the specific level for that feature, for that data point. Okay, so this is basically classical decision tree stuff. When the data point arrives at a node, it can only go left or right, depending on what features we branch on. For the nodes where we make a prediction, such as node 2 here, the left and right node arcs will have capacity 0. The data point cannot be routed left or right. Instead, it may be allowed to go to the sink. We will only allow the data point to reach the sink if the prediction made at the node matches the label of that data point. Okay. So basically, to summarize, if we forget about uncertainty for a moment, the branching and prediction variables that we have fixed for our tree are going to induce one graph for each data point. And now deciding whether that data point is correctly classified or not reduces to checking whether it's possible to build a path from source to sink for that data point, right? So whether basically we can have a flow of one for the graph associated with that data point. So for example, data point here on the left is correctly classified because I can build a path for source to sink through which the data point can travel. What happens with uncertainty though? Well, if I have uncertainty, now we have an adversary that can come and perturb the features of our data, which means that it can basically change how the data point is routed when it enters different nodes, right? So for example, here, this adversary can come and change the feature on which I was branching on, and so therefore change where this data point is routed, and instead of allowing it to go left, now the data point will go right. This time we can no longer have a flow of one through this perturbed, basically, graph, and so this data point becomes incorrectly classified. Okay. So putting these ideas together, basically, once we fix the tree encoded through the variables BVW and the perturbation, deciding, remember, whether a data point is correctly classified or not corresponds to seeing whether I can have a flow of one through the graph induced to that data point. And so we can just, to compute the accuracy of our tree for fixed perturbation, we just need to solve a maximum flow problem that basically collects the flows for all data points and tries to make them as large as possible. So here my flow variables, I'm going to call them Z, and I'm going to try and maximize the flow of data points from any given node to the sink node Z. And these constraints are just the flow constraints, basically the associated with all the data points. So what do they say? Well, naturally, at all nodes for all data points, we have flow conservation, which are these two constraints. And then the other constraint fix the capacity as appropriate based on the feature values and the branching decisions, right? They basically fix to 0 the capacities of the arcs along which my data point cannot travel. All right, so we had this original formulation. What have we achieved? We have achieved that we have obtained an equivalent reformulation of our complicated problem as now a two-stage robust optimization problem with mixed integer decisions, basically. Why? Well, I've replaced the outer maximization over pi as a maximization over the BVW variables and optimization over an integer set, right? I've kept the inner minimization unchanged, and now I'm representing the accuracy of my problem as the optimal value of this maximum flow problem. So this is now, for this robust optimization community, a two-stage robust optimization problem with a small complication that this set T is discrete, okay? Yet perhaps because everything is linear, perhaps there's something we can do. So now let me move on to our solution approach. So here I've rewritten my two-stage problem. And recall that this inner maximization problem is a maximum flow problem, right? So I can relax integrality over the z variables and use duality theory, right? So now I'm gonna do this duality step in the next slide. My dual variables, I'm gonna call them Q. So these are the decision variables of a minimum cut problem. And I've grouped the decision variables Q and the adversarial perturbations C under the same mean. So now I have a single stage robust problem, but arguably it is a little bit complicated because it does involve products of those Q variables with indicators involving the X's, so it's perhaps not obvious how to solve it. The first step we're gonna do, and let me just take a step back for a moment, right? So we still have in the outer structure, in the outer maximization, a decision on the tree structure. This has not changed. But in the inner problem, now we try to identify the worst case shift in the data and the associated minimum cut. Okay. We can write this problem using its hypograph reformulation. Again, in principle, what makes this problem challenging are these products here and the fact that we have a potentially large number of constraints. And our idea is to solve it using delayed constraint generation, whereby we're gonna optimize in the main problem over the structure of the tree and the hypograph variable t. And then in the subproblem, we're going to try and identify realizations of Q and C to add to the to our main problem, and we're going to iterate in this fashion. This is pretty standard, probably, for this community. What is interesting is how we solve the subproblem, and I'll discuss this in a moment. So just to summarize here. In the main problem, we're going to optimize over the features to split on and the level of the feature to split on, and then our labels. In the subproblem, we're going to identify a worst case perturbation and a minimum cut. This is going to help us identify violated constraints in the main problem that we're going to add iteratively. So what is interesting is how we solve this subproblem. I'm going to tell you at the high level how we solve it. Basically, the idea is to show that it suffices to look at some feasible cuts that are candidates to be optimal in that problem, and there's polynomially many of those, so we're just going to enumerate over them, and then we're going to identify the corresponding perturbation by solving a problem that tries to look at the minimum cost way of perturbing the data in a way that the data point will flow in a way guided by the corresponding cut variables. This will enable us basically for each data point to find the minimum cut cost of misclassification for it. Then we're going to sort the data points by misclassification cost from smallest to highest. And then we're going to basically start perturbing the data points until we run out of budget. And this will help us identify the worst case for any given tree. And it's gonna help us basically identify violated constraints to add to the problem. So earlier I talked about our uncertainty set, but I didn't mention how to calibrate it. Here we propose an idea for calibrating the uncertainty set based only on knowledge of the probability that our data will not be perturbed. So if all I know is the probability that for given data point and feature, the data point will not be perturbed, it makes sense to assume that our perturbations follow a symmetric geometric distribution. What this says basically, right, is that we have the QIF would be the parameter of our distribution. The larger QIF, the greater the probability of certainty, right? The smaller QIF, the lower the probability of certainty, and this gives us basically a probability for each realization of the shift. We can then set up a hypothesis test, and this gives us basically an uncertainty set once we fix the parameter of that test. This says that on the numerator, we have the likelihood of a particular deviation, C. In the denominator, we have the likelihood of the maximum likelihood realization. And here we say we want to basically hedge against all realizations, C, that are within lambda of this maximum likelihood. The reason why we have the power here is just for normalization across data sets where some may have more or fewer data points. And after a little bit of work, we obtain basically an uncertainty set in the form I highlighted earlier, where this parameter here gives me the gamma, the unit cost of perturbation, and this right-hand side gives me the epsilon. There's ways to generalize these to categorical features, to features that are integer but bounded, to binary data and whatnot. I will not bore you through with this, but the idea is the same. And I see there is a question in the chat. Yes, any specific reason for choosing perturbations following symmetric geometric distribution? Yes, this is a very good question. This is the maximum entropy distribution if the only assumption that I have is that I know the QIFs, the probabilities of certainty. So it kind of makes sense. Did I answer your question? Okay. All right, so let me now move on to some numerical results. Oh, sorry. Yes, okay, looks like I answered it. Okay, numerical results. So, sorry, this starts a little bit abruptly, so let me tell you what we did. So, what we did is we took basically all data sets from the UCI machine learning repository that had the discrete data. And then we learned our tree for various values of lambda, where lambda is basically the right-hand side of my uncertainty set that tunes the degree of robustness. And here we're showing, as we vary lambda, the smaller lambda, the more robust our problem, we show the difference in the worst case accuracy less of our approach, less the worst case accuracy of non-robust classification trees. Okay? So what we'd like in this graph is to be as high up as possible. We did two sets of experiments. One is where the perturbation is as expected, meaning that we got those probabilities QIF correctly. And one where we have unexpected perturbations, meaning that, you know, we didn't estimate this correctly, so we have kind of unexpected shifts, different than what we had planned. What we see is that for most of the range of lambda, we have an improvement over non-robust trees, right? That's actually relatively high, up to 10 percentage points on average. We also see that across all data sets, there seems to be a consistent choice of lambda that is quite good, somewhere between like 7.5 and, 0.75, 0.85. So we can kind of safely make that choice. In the next slide now, I'm showing what happens in terms of the average accuracy. And we see again, so here we're comparing again the average accuracy of the robust approach versus the average accuracy of the non-robust approach. Again, we see that for a large range of lambda, we are greater than or equal to 0. And in particular, for the choice of lambda 0.85, we also improve in average case accuracy. So this seems to be perhaps a good choice overall to improve both worst case and average case accuracy. What happens in terms of solver times now? So this is a performance plot. On the x-axis, we're showing on the left side solver times. And on the right side, we're showing optimality gap for those instances that basically did not solve to optimality. On the y-axis, we're showing the number of instances. So how do you read this plot? Basically, this is showing the total number of instances that solved within a particular time, right? On the left side of the plot. And then on the right side of the plot, it shows the total number of instances that had an optimality gap no greater than the value on the right side. So what you want to be in this graph is, again, as high up as possible. What we're showing here is different lines for different values of lambda. the results kind of make sense. The less robust our approach, so lambda equals 1 is the non-robust case, the more instances we're able to solve. So kind of there's a price here to pay. In trying to be robust, you have greater solver times, greater optimality gaps, and whatnot. We've packaged both this work, so for learning decision trees that are robust to distribution shifts, and then other works we have on learning optimal classification trees, on learning fair classification trees, on learning optimal prescriptive trees in this ODT Learn Python package that I encourage you to try. We have a corresponding paper in preparation for submission as well. I'd like to acknowledge funding support from the NSF through my career award, and then Nathan Justin was actually supported through the NSF Graduate Research Fellowship Program, so we're grateful for their support as well. The work I presented is based on a paper we're preparing for submission to Operations Research, but we also have a preliminary version that's available online that has appeared in a AAAI workshop on adversarial machine learning and beyond. Thank you all, and we have plenty of time for questions. I'm happy to take them, and there is one in the chat actually.
Yes, so thank you so much, Phebe, for the very interesting presentation.
Thank you, Reza.
What we can do is stop recording and have a